All right, let's do this thing. So, questions from homework 4, Jack. What do you got for us here, sir?
Any 5 through 8.
Okay. Does anybody else have a preference on 5 through 8? Enzo? 8, you say? Okay. All right. So the idea here, the first thing I'm going to do is I'm going to take my factor that I'm given, set it equal to 0, and solve. Because that's the number that's going to go on the outside of my synthetic division. The inside numbers in my synthetic division are going to come from the polynomial I'm trying to factor. But before I start writing those numbers in, take a close look at that polynomial. You'll notice that we go from x to the 6th to x to the 5th or 4th. We skip the x to the 5ths. And the same thing from x cubed to x, we skip the x squared. So we're going to need to make sure we include those zeros when we do our synthetic division setup. So we have 1, 3, 0, -7, -28, 0, -8, and then -24. So far, so good, Jack? Enzo, you good so far? Okay. Those zeros are important. You will not get the correct answer without them. They're easy to forget about. So please make sure you're being careful when you're setting up your synthetic division to take a quick look and make sure you're not skipping any, that you're not missing any terms in your polynomial. So the first step in synthetic division is we take that first number and write it underneath. And now from here on out, we're going to take the number on the outside, multiply it by the number on the bottom, write it in the next empty spot, and add down. So -3 times 1 is -3. And then I add down 3 plus -3 is 0. -3 times 0 is 0. Add down, I get 0. -3 times 0 is 0. I add down, I get -7. -3 times -7 is positive 21. I add down, I get 0. -3 times 0 is 0. I add down, I get 0. -3 times 0 is 0. I add down, I get -8. And -3 times -8 is positive 24. I add down, I get 0. So far, so good, fellas? Okay. So this last value being 0 is what I expected. Since that gives me a 0, I know that x plus 3 is one of my factors. Since the x plus 3 is what I did the division with. So I know automatically that's one of my factors. My other factor is going to come from the quotient. So starting at the right, that's the constant term. My x coefficient, my x squared, my x cubed, x to the 4th, x to the 5th, and then x to the 6th coefficient. So my other factor is x to the 6th minus 7x to the 3rd minus 8. I didn't bother to write in all the zeros there for obvious reason, right? Okay. So we've done with the division part. What we need to do now is check to see if we can factor the remaining pieces using our factoring tree methods. Hi, Riley. Thank you. And if I look at x plus 3, that's linear, so I can't do anything with that. But the x to the 6 minus 7x cubed minus 8, that looks like something that maybe I can do. I can factor more. So looking at that, I notice it's 3 terms. It's in the quadratic form. Its leading coefficient is 1. So I should be able to use the short factoring method on this. So I'm looking for 2 things that multiply to give me -8 and add to give me -7. Well, that's -8 and positive 1. And I know that instead of x's, I have x cubed, because that's like the middle x in my thingy-majigger. So far, so good, Jack? Enzo, you good still? Okay. Now I need to check out these little guys to see if I can factor either of these. So they're both two terms. Neither one of them is a difference of two squares because the exponent is odd. But it definitely looks like the first one is a difference of two cubes. Right, I can write x cubed as x to the third. And 8 I can write as 2 cubed. The other one, not a difference of two squares for the same reason, but that is a sum of two cubes. Right, I can write that as x to the third plus 1 to the third. So now I'll just fire up my difference of two cubes factoring pattern and sum of two cubes factoring pattern. If you haven't memorized these yet, you've used them enough times that you should be getting close, right? So the first one, my a is x, and my b is 2. So that gives me x minus 2 times x squared plus 2x plus 4. And the other one, my a is x, and my b is 1. So it gives me x plus 1 times x squared minus x plus 1. And I know that the linear pieces I can't factor anymore. And these quadratic pieces that come from the sum or difference of two cubes factoring patterns, I know I can't factor anymore. So my final answer is going to be the x plus 3 from way up there. And then this stuff, the x minus 2, the x squared plus 2x plus 4, the x plus 1, and the x squared minus x plus 1. That was by far the worst one of the 6 through 8 or whatever, the 5 through 8. Had the most to do after you did the synthetic division. I think the rest of them were fairly less, had a lot less to do, right? That one had a pretty significant factoring tree piece to it after you were done. The other ones I think were you spent much less time in the factoring tree on the other ones. But the important step here, the part that we really want to have the takeaway with, was that step right there, which is the one that we'll kind of be building from in the future, in this next lesson coming through today. So that's the step that we really need to make sure that we're comfortable doing and competent doing, because we'll be using that idea a lot today. Happy to do some more if there are some other questions. Does anybody else have ones that they want to look at from this? Lily. Sure. Okay. So the first thing we do is we look for a greatest common factor. So if I look at that, 972, that looks suspiciously like something that'll be divisible by 12. Not quite, but it is divisible by 4. Oh, 972, I typed to 976. Let me try that one more time. Yeah, so I can take a 12 x squared out. You good there? Okay. So next I notice that this is two terms. And under the two terms, next thing we check, is it a difference of two squares? Well, that seems likely because it's an even exponent. So let's try that. So we have 2x squared. X to the fourth is x squared squared. And 81 is 9 squared. So I can write this as x squared plus 9 and x squared minus 9. So far, so good? Now, x squared plus 9 is 2 terms, so I should check if I can factor that. It's not a difference of 2 squares because it's addition. And it's not a sum or difference of 2 cubes because the exponent on the variable is indivisible by 3. So that piece is as good as it's going to get. The x squared minus 9 is a difference of 2 squares. We should recognize that as like a first semester factoring problem. So let's factor that to x plus 3, x minus 3. And I know that those each can't be factored anymore because they're linear. So that's as good as we can do. Is that okay?
Yeah.
Making sure to get the whole 12 out of there at the first step really makes a big difference. If you had missed that and only took out 2 or 3 or 4 or something, or 6, you'd have been left with something that you probably weren't sure what to do. So it is typically when I check a problem like that, the first thing I'll do, Lily, is just see if the entire 12 will go out before I start looking, oh, I can take a 2 out. You know what I mean? Just because if I can do the whole thing, like, let's just do it in the beginning and be done with it. You know what I'm saying? Okay. Again, happy to do some more if you guys have some more you want to talk about here. If you don't, that's okay. Again, it's all about what you guys need, not me. I already know how to do all this stuff, so it's not a big deal. But if there's ones you're curious about or weren't sure about or just need to, you know, feel like I could use another example, that's cool too. Grudes.
Can you like 5, 6, or 7?
Yeah, does anybody have a preference on 5, 6, or 7? Okay. Well, let's just do 5 then. We'll do kind of a basic one because sometimes it's a little easier to get a handle on the method if you pick the easier problem to do, right? Because that sounds like what all we're really looking for is another run through on the method. So again, my first step is to take that factor, set it equal to 0, and solve. That -2 is what's going to go on the outside of my synthetic division setup. The inside of my synthetic division setup is just going to be the coefficients from the polynomial I'm trying to factor. So I don't have any skipped terms because I have an x cubed, an x squared, an x, and a constant. So I can just put those right on up there. So 1, 7, 14, and 8. The first step is to bring that first number down. And then I take the number on the outside, multiply the number underneath, put it in the next empty spot, and add down. And just keep repeating that process until I've run out of spaces. So -2 times 5 is -10. 14 plus -10 is 4. -2 times 4 is -8. 8 plus 8 is 0. Got that remainder 0, which I was hoping for. So that tells me that I have x plus 2 as my factor. And my other factor is going to come from this piece. So constant, x coefficient, x squared coefficient. Elizabeth, is that okay to there?
Yes.
Okay. I know I went kind of fast, so I'm pausing here to let that soak in for a second. But if you're okay, that's good. Now all I have to do is check to see if I can factor either of those pieces. Well, the x plus 2 is linear, so there's nothing I can do with that. The x squared plus 5x plus 4, though, that looks suspiciously like something I can deal with. In fact, that looks a lot like a first semester question, right? A first semester factoring problem. And we can treat it that exact same way. We just find the two numbers that multiply to give us 4 and add to give us 5. That would be 4 and 1, right? So I just bring down the x plus 2 still, and then I can write that as x plus 4 times x plus 1. Everything is linear, so I know I'm done. And that's all she wrote. Much easier than 8, right? Because the factoring after we did the division was considerably easier than that other problem. Although you see the first step was still identical, right? You do the synthetic division to factor it partially, and then you continue factoring the pieces that remain. You're welcome. Yes, Lily.
Oh, so I have one question on number 5. If it was x plus 2, why did you put negative 2 when you were,
So the start to do the synthetic division, the process is just to take whatever we're dividing by, set it equal to 0, and solve. So that's where the negative 2 is coming from, even though it's an x plus 2.
Okay.
When we go back and put the factor in, we're using the factor. So that basically it boils down to the sign is always the opposite. Does that work okay for you?
Yeah, thank you.
Yeah, of course. Okay. Do we feel a bit better about this assignment here after taking some time and going through it? We certainly did, I think, the hardest one, which I think was probably 8, at least the longest, right? There's a lot to do on 8. And we did a couple of the other examples, which is nice to go back and look at some simpler examples where it's a little bit easier to kind of see the separation of the two methods. Okay? All right. So today, we're going to continue kind of talking and try to figure out what do we do if we're not given a factor. So for example, in the homework last time, oops. We were asked to do a problem like this, right? And this was number 5 that we just did a moment ago. What we're going to look at now is what if we take that away, that starting place away. So what we're going to be trying to answer today is we're going to be looking to how do we pick a factor to start with. If we're not given one in the problem, what do we do? How do we find one? How do we pick one? Now I'm going to be up front with you. To some extent, there's going to be some guesswork involved. But over the course of the next 2 lessons, we're going to look at some definitions and some theorems to kind of help us remove as much of that guesswork as possible. But on occasion, you're going to run to a place where you try to do a synthetic division and it doesn't work. That's okay. It just means that whatever factor you tried didn't work and you'll have to go and try something else. But the goal here, as we develop these extra tools, ideally, before we even start trying to do the synthetic divisions, we should have a good idea of whether that is going to work or not. But right now, you don't know that because you don't have any of the tools or definitions or anything built out yet. But that's what we're going to be doing over this lesson and the next. Okay? So just kind of keep in mind that the question we're trying to answer is like, how do we figure out what to start with? Okay. So the first thing I want to do is just cover some vocab. So there's 4 terms that are all fairly related or semi-related that I want to make sure that we're clear about. Okay. So our first definition says that x equals a is a solution to the polynomial equation f of x equals 0 if and only if f of a is equal to 0. This should kind of remind you, although like symbolically looks a little confusing, but this is basically what you would have done when you first were introduced to algebra in your pre-algebra class, right? If you solve 2x minus 6 equals 0, and you get like 3 as an answer, probably what your teacher told you to do was then put 3 back in for x to make sure it works, right? You guys remember doing that way back in pre-algebra? That's all this is saying. It's saying if we have a solution, when we plug it back in, it has to give us 0. And if we have a number that we can plug in to get 0, we know that's also a solution, right? That's all we're saying. Is that okay? So it's like a pre-algebra concept there. And by the way, that IFF is the abbreviation for if and only if. So the next one says if x equals a is, or x equals a is a 0 to the function y equals f of x, if and only if, when we plug a in, it evaluates to 0. So the next definition says a is a root to the polynomial f of x, if and only if x minus a is a factor of f of x. That's basically what it's saying. And the last one says that a is an x-intercept of the graph y equals f of x if and only if the point a comma 0 is a point on the graph of y equals f of x. So remember, x-intercepts are where the graph crosses the x-axis, right? If something's y-coordinate is 0, that means it's on the x-axis. Everybody okay with that idea? Okay. So let's kind of sift through this information here and kind of talk about the relationship between these two things. Okay. So every x-intercept we know is going to be a solution, and we know it's going to be a 0. However, the reverse is not true, that every solution or 0 is not going to be an x-intercept. What's the issue there? Is that zeros and solutions can include imaginary things. And when we graph, there's no imaginary stuff to put anywhere to place the imaginary things on the xy axis. So every root is a solution, a 0, and an x-intercept, but the reverse is not true. So the issue there would be the imaginary things and the irrational things. Okay, so far so good. So the takeaway here so of these 4 things, well, I can leave that. Solutions, zeros, roots, and x-intercepts, which one of these will be the easiest for us to find? It's going to be the x-intercepts. Why? You can just graph it on your calculator and look at the picture, right? Doesn't require you to do anything other than that. Everybody agree with that? So what we're going to use in part of this process is we're going to use our calculator to identify x-intercepts. and we'll kind of use that as part of our information. But we need to be careful here because every x-intercept is not necessarily going to be a root. And the roots are what we're going to be using to do our synthetic division with, right? Because the roots are basically going to be the same information as a factor. So we're going to need more than just this idea in order to be able to sort through every situation. Joseph?
Yeah, what's the word after x-intercept?
That's just calc.
Okay.
Like calculator. So we're going to need some more information than just the x-intercepts. So we're going to add on some more theorems here. And we'll look at, what I think, 4 of these today, and we'll stop. We'll make up a method to do our factoring that's complete up through this information. And we'll add on to this information next time because, well, there's some situations that are not going to be easy to handle with just this, with just the method that we'll develop up through today, that we'll need to add on some little bit of extra information to kind of sort through the rest of it. Okay with that plan? Okay. So the first theorem is called the fundamental theorem of algebra. And with a title like that, you can rest assured it's going to be pretty important. But it's a pretty simple statement. It just says that every polynomial is solvable. So they all have solutions. That's it. That's the whole statement. Now this is an important result in mathematics. This was something that was kind of the central question, or the most important question in mathematics for a long time, and really the best mathematicians of their era kind of took a crack at this. The man that finally proved this, his name is Carl Gauss, and he did that in like the 1700s. It's now, and actually it's fairly easy to prove with calculus, but that didn't exist at the time where they were trying to prove this, in which he did prove this. So maybe one of the most important mathematicians of that Renaissance era. So anyways, it just says that all these problems we can solve. And if we can solve it, we can factor it, because we've shown earlier that those two are basically equivalent, right? If we have the solutions, we can go and make the factors, and if we have the factors, we can get to the solutions, right? We've done that back and forth. The next one is the corollary to the fundamental theorem of algebra. And the corollary here says the number of solutions to a polynomial equation is equal to the degree of the polynomial. And then I have parenthetically saying that as long as you're counting all the complex solutions and all the multiplicities. Now, the multiplicity is probably something that you're not familiar with. So let's just kind of show you an example, because we've encountered this already before. Let's say we're back in first semester, and we're solving something like x squared plus 4x plus 4 is equal to 0. You could solve that by factoring, right? That factors to x plus 2 times x plus 2. You can then set each of those equal to 0 and solve. And you get that x is equal to -2. Twice, right? So what we say is the solution is x is equal to -2 with a multiplicity of 2. Basically, that -2 counts as 2 solutions because we got that solution twice. Even though it's the same number, we need to count it 2 times. If we do that, the corollary holds at strict equality. Is everybody okay with what we mean by a multiplicity? So it's something we've already encountered, right? We just didn't call it a multiplicity when we'd encountered it. But basically, as long as we're counting all the imaginary stuff and all the duplicate solutions, that will match up with the degree. So we know exactly how many solutions we should be looking for, which is nice, right? You know, like we've seen, the polynomials can sometimes have lots of answers. It's good to know how many total answers we should be finding. Cool? Okay. The next tool is called the factor remainder theorem. And we've already talked about this, we just didn't use the name for it. It says that oops, I think we want to probably write that in minus. So this just says that x minus a is a factor of the polynomial f of x, if and only if f of x divided by x minus a has remainder 0. This is basically what we were using last night in the homework, right? Where if we can do the division, that tells us that we have a factor. Everybody cool with that idea? Okay. And then the big tool that we're going to be using today is called the rational roots theorem. The rational roots theorem says that if f of x is a polynomial with integer coefficients, then the rational solutions to f of x are of the form plus or minus a factor of the constant term divided by a factor of the leading coefficient. So let's just this is the important one today. So let's just kind of illustrate clearly exactly what this is saying. So remember from the homework, we had factored this polynomial, x cubed plus 7x squared plus 14x plus 8. It factors to x plus 3 times x plus 4 times x plus 1. Right? You remember doing that? We did this together in class as an example at the start, or a question, but this was in the homework assignment from the previous night. So note here that my solutions are -3, -4, and -1. Each of those are rational numbers, right? Because they could be written as a fraction, like -3 over 1, -4 over 1, -1 over 1. So what I can do here is, using the rational roots theorem, I can say the possible rational solutions for this polynomial are going to be involving the factors of the constant term, which is 8. So the factors of 8 are 1, 2, 4, and 8. And the factors of the leading coefficient, which are 1, which is 1, and the only factors of 1 is 1. So my possible rational solution should be plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, and then plus or minus 8 over 1. Where the denominator is my factor from the leading coefficient, and my numerator is the factor, or is a factor from the constant term. And my takeaway here is, this was a 2 or something, wasn't it? I wrote down that wrong. That couldn't have been a 3. That had to be a 2. I'm so dumb. That's what I get for trying to remember what I did 25 minutes ago or something. That's probably longer than that. But the takeaway here is -2, that's on my list. -4, that's on my list. -1, that's on my list. Right? So here's the big takeaway. We're going to start with some polynomial that we don't have any idea what the factors are. We can use the fundamental theorem of algebra to know how many solutions that we should be looking for. We can use the rational roots theorem to figure out the possible rational solutions. And then we can check the graph for the x-intercepts. Any x-intercepts on our graph that agree with the possible rational solutions on our list are good places to start our division with. So let's do a couple of examples here to kind of get us familiar with this method. Okay? Well, that's fine. I didn't want it to be red here. So let's say we just ask you to factor x cubed minus 19x minus 30. Should be pretty clear that you can't use our factoring tree method on this. although it is 3 terms, it's not in the quadratic form, so there's nothing we can do with our factoring tree. Everybody agree with that? It's always worth taking a quick look to see if, like, hey, maybe I can just, like, knock this thing out using the factoring tree, which might be easier for us, but we can't. So using the fundamental theorem of algebra, I know that this could have would have 3 solutions. Because the degree for this polynomial is 3. Everybody okay with that? So my possible rational solutions then, I can find by looking at the factors of the constant term, which is -3. So those factors are just 1 and 3. And the factors of the leading coefficient, which is 1, those factors are 1. So my possible rational solutions would be plus or minus 1 over 1 and plus or minus 3 over 1. Oh my goodness. That was -30, not -3. Jeepers creepers. We missed so many. 5, 6, 10, 15, 30. That's more like it. Okay. So that's my list of possible rational solutions there. Yuck, because what's that? That's like 20 things to possibly have to check by hand. We can narrow that down by looking at our graph. So I'll fire up our calculator. So if you want to kind of follow along with the calculator portion with me, that's cool. If you don't want to and you just want to sit and watch, that's cool too. It doesn't really matter. So the first thing we'll do when we take out our calculator is go to the y equals menu. So the y equals button is in the upper left-hand corner of your calculator. And then I'm going to go ahead and clear out anything I had in that y equals menu. So I had some stuff there, so I just got rid of it. Now I'm going to type in the polynomial here that I'm trying to factor exactly as it's written on my sheet of paper. So I have x to the third minus 19x minus 30. Okay. Now as a reminder, when we're going to graph this thing, the only thing we care about are its x-intercepts, right? And specifically, the only x-intercepts I care about are the ones that are on my possible rational solutions list, because those are going to be the only one that are feasible places to start my synthetic division with. So if I look at that possible rational solutions list, what's the smallest number on that list? It's not a trick question. Okay, so remember it's plus or minus. So really the smallest number is -30, right? Everybody's okay with that? The biggest number would be +30. So what I'm going to do before I graph this is to set my window on my calculator so I'm only really looking at the stuff I care about. So I'm going to press the window button, which is right next to the y equals. And I'm going to set the x min to be -30 and the x max to be +30. The x scale I'm going to leave at 1. If it's not 1 already, I'll set it to 1, but it probably is your default. And the y min and y max, I just need to be positive and negative numbers. So usually I do something that's fairly close to 0. I did -3 and +3, but it doesn't really matter. You could have like -5 and +5 or -1 and +1. All we really need to see is where the graph is crossing the x-axis. So I'm going to hit graph now. So all of the interesting parts of this all look like it's happening fairly close to the y-axis here, right? So I know that nothing over here I care about and nothing over here I care about. So I'm going to go ahead and change my window so it's a little bit easier to see what's going on. I'd estimate that from -5 to +5, I'm still going to have everything that I care about. So I'll reset my window. And now I can tell distinctly I have an x-intercept here at -2, at -3, and then out here at +5. Do you guys agree with that? So I'm going to write down that information. So I have -2, -3, and +5. And I'm going to go check to make sure that those values are on my list of possible rational solutions. So I have -2, I have -3, and I have +5. All agree. So any one of these values would be a good value to start my synthetic division with. It doesn't really matter which one you choose since they're all on our list. They all appear to be whole numbers. So they all would be good choices. I'm just going to start with -2 as the first one. Yes, of course. Everybody okay with that? So now I'm going to go ahead and set up my synthetic division, starting with that -2. So in the top, I'm right 1, 0, -19, and -30. Why did I include the 0 there? Because I was missing the x squareds. Very good. Okay, so you have to be careful on that still. And now I'll start my synthetic division. So I got remainder 0, which is excellent. That tells us this worked. So the -2 tells us that x plus 2 is a factor. And the quotient tells us our other factor is x squared minus 2x minus 15. And x squared minus 2x minus 15, it can be factored. That looks like a semester 1 factoring problem. Two numbers that multiply to give us 15 and add to give us -2 would be -5 and +3. And there is our fully factored form. Does that feel okay there? Okay. Let's do another. So let's say we want to factor x to the 4th plus 2x to the 3rd plus x squared plus 8x minus 12. Well, tells us we should be looking for 4 solutions. My possible rational solutions are going to be the factors of 12 over the factors of 1. So I skipped writing the factors of each of those and just wrote that. Is everybody okay with me doing it that way? Okay. And then we'll go to the graph and check out what we see. We'll reset our window to be -12 to +12. And then we'll hit graph. So what do I see here on my graph? I see -3. And I see +1. What do you think is odd here, though? How many x-intercepts am I seeing? 2. How many solutions should I be seeing? 4. Where are the other 2 solutions at that I can't see? What? Okay, they could be further out in the graph where they're not a rational value, like you could have like the square root of like 270 or something, and that could be a big number way out somewhere that we can't see it. Okay, so it could be that. What else could it be? There's a couple of other possibilities. Bianca?
Could they be overlapping?
So you could have a multiplicity where you have the same one of these answers occurring more than once. That could be happening also. Yep. And there's a third possibility. They could also be imaginary, right? You won't be able to see the imaginary stuff at all. Everybody okay with that idea? So we should expect one of those 3 situations to be occurring. Tomorrow we'll talk a little bit more about how we can tell if one of those 3 situations is occurring, or which one of those 3 situations is occurring, because you should be able to look at this and rule out 1 or 2 of them right away. But not yet, but that's okay. The point of this is that if we go and we look at we have the 2 things that we can see are on our list. That's the good part. So we'll start our synthetic division. We'll just pick one of them. I'm going to pick the 1 just because the computation is a little bit easier if I just use the 1 rather than the -3. You know what I mean? They're both the same. Why make your life more difficult, right? Okay. So we have that. Now we could factor this piece here using our factoring tree method. It has 4 terms, and if I take a quick look at it, I can tell it will be able to be factored by grouping. So I could do that, or what else could I do? Well, I didn't use the -3 yet, right? So I could factor that by grouping, or I can do another synthetic division. So I can take that quotient and do the synthetic division with the other piece that I haven't used yet, the other possible, or the other x-intercept that I haven't used yet. And I know the x squared plus 4, if I look at that and try to factor that using my factoring tree, that's as good as that can do, right? It's two terms. It's not a difference of two squares because it's addition. And it's not a sum or difference of two cubes because the exponent isn't divisible by 3. If I tried to solve x squared plus 4, you'll note that you'll get an imaginary solution from that. It should be relatively easy to notice that because you'll be square rooting a negative if you solve that directly. What do you guys think? Okay, so we're going to pause here for today. At this point, this is our method that we have to deal with things. So we can use this method for today. We'll add on to it tomorrow to help deal with the cases of, okay, what if we get some imaginary things going on or some multiplicity things going on? Is there a way that I can detect some of that information, or what else can I tell from this to make sorting through those situations a little bit easier? So your homework assignment, I'm going to copy in here real quick, is going to be this homework 5. So I give you 6 of these things to look at. So I ask you to factor the polynomial, and I ask you to include the number of solutions, like we've done, using the fundamental theorem of algebra, the possible rational solutions, like we've done there, the likely rational solutions, that's what we're looking at the graph and determining, and then all the synthetic divisions done and any factoring tree steps. Okay, so basically saying to show all the work kind of the way that we did in the examples. So this will be in Sunday's homework check for this coming Sunday. And yeah, does everybody feel okay about that? Okay. Well, that'll do for today.